Power to the truth. This is Margo, and this is Thursday, August 30th, 2018. And today I'm going to give you an Arctic sea ice update, and we're also going to be looking at Arctic cyclones, looking into what is a polar cyclone or polar storm, and what constitutes a polar storm. So I dug into that because I really didn't know when I did the last video, and so I wanted to bring that information to you so we could get some perspective on what's going on up in the Arctic with those two cyclones, or potential cyclones that Robert Fanny saw a couple of days ago, and then I reported on that. So we're going to get some perspective on that. But first, we're going to do our sea ice update. And we can see I have the picture from Climate Reanalyzer up here for Thursday, August 30th, and we can see that the sea ice is declining greatly up on this northern, all around the northern edge, and that's from the storm that's forming up there. And it's actually raining up there right now, and it's raining over here too. But we're going to be looking at that in a minute. But just to get some perspective on where we've been, let me just go back in my slideshow. I like to do this so that you can see where we came from. And that little bit of ice over here in the Beaufort Sea that had kind of reformed is now going away. And that's because of what's going on up there too. There's yesterday, the 29th. There's the 28th. So you can see a marked difference just in 2 days. Here's the 27th, the 26th, 25th, 24th, and the 23rd, which was a week ago. So you can see the difference here. So it's still declining, and it's warming from underneath. There's a new study that just came out, and Robert Fanny and some other people reported on it yesterday about how, because the ocean temperatures are getting warmer, so when they come up from the Atlantic and they're so much warmer, then it's eating away not only at the extent, not only at the edge of the ice or the extent, but that warm water is mixing with the colder water underneath this ice cap, and it's getting trapped under there, and so it's heating up from underneath. And it's changing, it changes the salinity. So as that changes, then the freezing level changes, and you know, it's the whole science of it. So that's what's happening there. So let me get back to where I was, and we'll leave that picture for there. And now we're on Climate Reanalyzer for today, and I've pulled up the North Pole here, and we can see the great decline as we were talking about. And we'll just go through the rounds here. This is the temperature at 2 meters above the surface. Here's the maximum, and so what we're seeing is it's cooling down in parts of the over the Arctic. Now this is the air over the Arctic, as you know, but we've got these other regions coming in that are much warmer. And here's Svalbard, here's Novaya Zemlya. It's up you know, in the 8 degrees Celsius range. And this whole area off the coast of Siberia, well, in fact, the whole Russia coast is heating up. You can see that. And then where it's coming through the Bering Strait and coming into the Beaufort Sea, it's heating way up. So, you know, we're not out of the woods, and we're not going to be out of the woods. And that's because you know, it doesn't just depend on one factor. It's a whole multitude of factors. Here's the 2-meter temperature anomaly, and that means that the temperature is warmer than it should be. And in this area, just north of Canada and this northern part of Greenland, that's all warmer than it should be. Then this huge area coming in, and that's where we're seeing one of those storms forming and coming in. It's much warmer. And over here, to the south of Novaya Zemlya, and then it's way hotter. It's much, much hotter up here near this East Siberia ice shelf. Oh, and just as another little tidbit, I just learned that Russia and China are moving in 300,000 troops to a little bitty town called Tiksi, and it's right down here. Oh, I think it's, yeah, it's right down here, right on, it's a settlement, but they have made a base there, and they're going to be doing drills. Russia and China, they're moving in 900 tanks and I don't know what all. I just saw that today too, but I don't have time to bring up the article and report on all that. You can look for that. So they're doing operations. They're going to be doing tests and military operations up there. So that spells trouble in the Arctic to me, and it spells military conflict, and you know, we've got trouble all over the place. I try to not get political too much in these discussions, but you know, it's in this area, so maybe the methane bomb will blow them up. I don't know. So here's our precipitation, and we can see that it's raining, and that's part of that storm that was forming. It's raining over Svalbard and all that area. And it's also, there's a big system down here that was on the tip of Greenland, and now it's moving up. Now, I can't report on every single system, and so, you know, I'm trying to focus on the Arctic, the sea ice, and if I take too much time going off on all these other venues, I just can't get the sea ice done. But there is a large system over here, but there's no ice that we're worried about chewing up. But there is a large system off the coast of Greenland, and people want to be watching that. And it's also raining up here off of Siberia. So, oh, I learned about sea level pressure too. I learned that like 1,000 millibars or HPA or millibars is kind of okay weather, and then as this starts dropping, so that's in the dark gray blue zone, which would be like out here, that's okay weather. But as it starts dropping, then it's also called sea level pressure, then that's when storms can form. And the lower it gets, the more intense the storm can be. And so we are seeing areas over the Arctic that are below 1,000. But right in the eye here, it's about 990. But we're going to look at Earth Null School, and it'll show us exactly what that low is. And then over here, this is on the southeast part of Greenland where that storm is, and then over here where our storm is forming, and then over here where it's raining, and over here too. So, and in that 2012 hurricane, I think it got down to like 960 or something like that. So that's below the readings on this chart. So we can see what the jet stream is doing, and we can see that it's high wind speed coming off of Canada below Greenland, so that's feeding into that storm there. And we have the jet stream coming over Svalbard, and then it kind of, I can't tell if it kind of splits. I think it loops around here. So it's a crazy, I do see a split though, because it comes down here and then we have another one coming here. So we've got a split up jet stream, it looks like to me. And I'm not a meteorologist, I'm just learning all this stuff. So I'm just reporting and showing you pictures. Here's the sea surface temperature, and we can see that. We can look at that on Earth Null School too. I think it's easier to see it on the map with all the colors though. I really like those so that I don't have to click here or click there and get the temperature. So we can see like the water coming up to the ice is all above zero. It's all above zero. So that means it's warmer. And it's much warmer coming in from the Atlantic, as we can see. We have the dark blue, which is 10, and then it moves down into the purple, which is 5, and then the dark purple, which is probably about 2, down to 0. This is degrees Celsius. Here we have the sea surface temperature anomaly. Now this is how much warmer the sea surface temperature is than it should be. We see it a lot warmer over here off of Siberia in that Laptev Sea area, and also over here, and see this warm area breaking right through, and that's what melted up that ice that had kind of formed in that Beaufort Sea. And then all the way around the edge here, and then definitely up over here on the east coast of Greenland where that storm is. So that's all I'm going to show on Climate Reanalyzer. I will leave my sea ice and snow cover picture up. We're now going to look at the Navy sea ice thickness for today, and we can really see how it's all breaking up over here on this west side, and it's really diminished here and is still diminishing on this eastern edge, and a little bit of ice is coming back here, but we're not out of the woods. A little bit of that thick ice, and when we run the 30-day GIF, you can see the diminishing sea ice. and you can see how it's going down to nothing, and this is where they're going to run that ship through, right through there. And it's coming back a little bit on the north coast of Greenland over here, and you'll see that on NASA Worldview when we look there. So next we're going to go, let's look at the sea ice speed and drift, and we'll get an idea of what's going on as well. So the speed of the drift is looking quite high, and it's in this circular pattern where that storm has been going for the last few days. So it's moving and drifting and moving and drifting, and so that's what's breaking it apart. And then this little part up here is moving to the south, it looks like. If you want to look at sea ice concentration, you can see the concentration is getting lower by the day. Okay, now we're going to hop over to NASA Worldview. This is what we have available for today. The data is still coming in. I can refresh this and see if any more data has come in since the last time I refreshed. And it looks like this area, there was some data missing up here over the land, and there's some data missing over here, but what we want to look at is this area in here, which we have pretty much all of that data. We don't have it on this little corner of Alaska. There's a lot of cloud cover going on because of the storms. Here's the cloud cover for the storm on the eastern side. Here's the cloud cover for that storm from East Siberia, the East Siberia Sea. But even with the cloud cover, some of it's quite thin, and so we're able to really look at the deterioration of the sea ice. I'm really interested in looking at this portion. This has been hanging on, and we're looking through clouds, remember. So, it's hard to tell what's cloud and what's sea ice. I don't see a lot of sea ice, frankly. I see a lot of blue water. And it's just quite webby and probably just kind of slushy, is my thought. And this will be, if it rains, if this storm is mainly rain, this will take care of this sea ice. And the wind doesn't have to blow very fast. All it takes is some rain and some warmer temperatures, warmer air. Here we're looking through. This, where my pointer is at 81 degrees north latitude. This is a little area without clouds, and then we're going back to clouds. So it's still breaking up. I don't, we're not at the end of the melt season, and I don't know when the end is going to be this year. It may be later. We may not have an end. From what we saw, and from some of the articles that I've read and the YouTube videos that I've watched, what happens is, as everything heats up, then once the melt season stops, it's longer before the refreezing starts up, and so it gives more time for this warm warm ocean water to come in and be eating away from underneath and from the edges. So basically the sea ice is diminishing year-round. It's dropping year-round. Even though there's a refreeze, the volume, the concentration, the thickness, all of that is dropping year-round. Here's a hole we can look at. Look at that. That's at 84.36 north. That looks pretty bad to me. That's all water right in there. That's all broken up. Here's some more. Now that's a cloud, but let's zoom in here. That's as close as I can get. So under these clouds, the sea ice is breaking up and spreading out because of that wind that's been going round and round and round for I don't know how long. I really haven't been watching that. I guess it's something I need to add to my list to watch. And I will if I need to. It helps us understand the fragility of this ice. And there is some snow coming down. There is a little bit of snow cover on the ice. Now look at this area. That's very broken up. Okay, here, that's at 88 degrees, 88.39 degrees north latitude, and 90 is the North Pole. And then it goes into clouds. So it probably just continues like that under all these clouds that we can't see through. That's a huge area that we can see today. And moving on down, here's some more. That hole is at 86.57. I'll just follow this area, and then here's that northern part of Greenland. Here's Cape Morris Jesup. Then there's clouds, I think. Yep, there's clouds. We can't see what's there. It might have refrozen a little bit of thin ice. And here's another opening in the clouds where we can see more. This starts on to the Canadian part. You can see this was some of that old sea ice. So I'm not going to spend a lot of time over here because it's so covered up with clouds. There's not a lot to see really. I mean, we can peek through and we can see areas here and here. This was part of the old sea ice. But this is all cloud cover. We can't really see that much. So now we're going to move on over. Well, let's take one last look here. Yeah, that's too cloudy to really tell anything. But that's just lacy. The ice is just, you know, it's a long way between those chunks, I'm sure. So, there's NASA Worldview. Now, let's hop over to Earth Null School. And what I was going to show you this is the image of what we thought these two areas, these two storm systems, were, how they were going to be developing in the Arctic by tomorrow, by Friday, August 31st. And you'll see it hasn't quite happened that way. So this is why people who try to forecast weather are wrong a lot of times, because you just don't know, you know, what the wind is going to do, what the temperatures are going to do. I mean, there are a lot of different factors involved. And I think also the fact that we looked at it 2 days ago, our intention for it to be not as dramatic might have changed it. In quantum physics, the observer affects the experiment. And so by us bringing this information to you, our audience, and everybody looking at it and saying, oh no, that'd be so terrible and we don't want that, our intention, we made a mass intention. It was like, oh, that would be so terrible. Oh no, look at that, look at that. And with that, that's our consciousness and the mass intention, and our mass consciousness going out could have changed the route of these storms and the intensity of these storms. And now I'm going to show you how it's developing. So here's Earth Null School from today. Right now we can see this storm down here at the tip of Greenland, but I'm not going to spend a lot of time on that, as I said. But it is feeding into all the systems coming in up here. So now I'm going to zoom in. I'm going to put my pointer right here. Actually, let me go back. Okay, I think it got it a little further to the right, so that I don't know why they designed this like this, because the Earth is over here on the left, and when you blow it up it just goes further to the left, and then you pull up this little graph and chart and it covers up half of it. Why did they do that? Someone needs to move that Earth over to the right, and you know, if there's a way to do it, you know, I would appreciate someone letting me know in the comments. But right now, you know, that this whole thing just covers that up. And you know, I've spent some time on Earth Null School now, and I find it kind of frustrating to use. It's hard to use, and I like colors like Climate Reanalyzer and CAMS, and I like the satellite imagery from NASA, and I like the, you know, I like the things where I don't have to be, you know, closing this, and now I can see what I want to see. So right now, what we have, this is at surface level. We still have this area circling around. It's not very fast. It's 8.2 meters per second. And that equates to 16 knots, 18 miles an hour, or 30 kilometers per hour. But it doesn't take much of a wind or a breeze to be washing this warm air over this ice, and it's melting. Okay? And then the system over here Okay, so the picture I showed you was for tomorrow. What we thought was the forecast from Earth Null School, how they thought everything was going to go, and so this system here it is today, and it's still down here by Svalbard. So, and the speed is 12.6 meters per second, 11.3, 14.5. And the reason I'm using this meters per second is when we get into when we get into the definition of cyclones and this and that, the only chart that I could find measuring these different speeds and kind of putting them in a category, it was meters per second or knots. So I chose meters per seconds, and that equates to 28 knots, 32 miles an hour, or 52 kilometers. That's not real fast in my mind. That's just not real fast in my mind. Some people think it is. So, here it is right now. So now I'm going to pull up the thing that covers up half the Earth here. And we're going to advance this. Here it is tomorrow. And what we can see, this, and I've got it on local time, 2100. That's my time. So 2100 Pacific time. And if you want to switch it to oh no, it's UTC time. Okay. We'll just leave it there. 2100 UTC time. It's going to look like this, they say. And we can see that this system coming down from Siberia, instead of it being more over the ocean, it's now coming down and going over Alaska and losing speed. And I'm not a meteorologist, so I don't know how to say all of this. I feel like a weather girl here. And we still have this other system that's circling, but it's been pushed down and it's a lot slower. See, that's 7.7 meters per second. So now over here on this bright spot, that's 18.2 meters per second. So at the fastest, 18.4, 15.9. I've got a cough, hold on. Okay, so we were talking about this wind speed, and just for the heck of it, let's see what the wind speed is down here near Greenland. That's 19.8 meters per second, 39 knots, 44 miles per hour, and 71 kilometers per hour. .73 kilometers per hour. So the fastest part is about at 73 kilometers. See, this is why I find that Earth Null School kind of frustrating to use, because you can't find the exact same. Okay, you can't find, well, where's the highest? Here's 76, so let's take that reading. You know, I might get better at it and enjoy it a little more, but at this point, you know, it's frustrating to me. 47 miles an hour. So, and then up here, oh, we looked at that. Here's 29 miles per hour, 27, 34, 39, 39, 41. I think that's the fastest I've found. .4 meters per second. So that's for tomorrow. And then you can advance it 3 hours at a time by hitting this little comma. You go back 3 hours at a time by hitting that little comma. And then you can go forward 24 hours by hitting that arrow, that double arrow. So I always give instructions so people can figure out how to use this themselves. So I'm going to leave that up, and now we're going to learn about cyclones, because frankly I didn't know anything about them, and I saw that Valhalla left a comment saying, you know, I don't know about cyclones and if this is unusual or if it's this fast or what's bad and all this stuff. So in the meantime, I looked it all up, and now I'm going to share my research with you. And we're going to start with simple English Wikipedia. Polar cyclone. Polar cyclones, also known as Arctic cyclones, are large areas of low pressure. They should not be confused with polar lows, since people happen to use the same term for polar cyclones. Polar cyclones are usually 1,000 to 2,000 kilometers wide, in which the air is moving in a spiral counterclockwise fashion in the northern hemisphere. The reason for the rotation is the same as tropical cyclones, the Coriolis effect. They also exist in places such as Greenland, the Eurasian Arctic Sea, and northern Canada, with about 15 cyclones per winter. Polar cyclones can form in any time of the year, although summer polar cyclones are usually wetter than the ones that form in the winter. Oh, weaker. I misread that. Are usually weaker than the ones that form in the winter. Also, they are not closely studied and are rarely destructive, since they happen in areas with little or no population. I think they meant rarely destructive to humans. I mean, they can be destructive to sea ice. So, and it says one center is near Baffin Island and the other over northeast Siberia in the southern hemisphere. Northeast Siberia. In the southern hemisphere, it is usually near, I think they meant to say they center, or one's center is near. You know, the way they write these things, it makes me crazy. In the southern hemisphere, it is usually near the edge of the Ross Ice Shelf, near 160 west longitude. And we know where that is, because I've shown you that in my Antarctica video. Next, we're going to look at the National Snow and Ice Data Center. And here, an Arctic hurricane. And here is where they were reporting on an Arctic hurricane in November of 2011. And this is the satellite image from November 8th of 2011. And it shows a hurricane-like storm that hit western Alaska earlier that month. So we really don't see anything like that, of that magnitude, from NASA worldview. So I would not consider these cyclones. And I don't know why Robert Fanny called them cyclones, but you know, he has his reasons. But now that I'm looking into it and having a chance to look at the data and see how everything is moving and forming and all of that, I would not call what we're looking at cyclones. So I do expect some deterioration of the sea ice from these storms. It's not going to help them any, but I wouldn't call them cyclones at this point. Storms, climate, and sea ice. And this storm from November of 2011 was unusual because it occurred so early in the winter, before the sea ice had formed into a thick covering that can dampen waves. Some media coverage of the storm suggested that less sea ice covering the ocean left the coastal areas more vulnerable to the storm than they would have been otherwise. But in the region where the storm hit, sea ice extent was actually pretty close to average for that time of year. So while sea ice continues to trend strongly downward on average, this did not play a role in the storm's force. It was the timing of the storm that made it so destructive. Storms this strong don't typically happen this early in winter, Nelson said. Such storms may form 3 or 4 times in a winter, but the Bering Sea coast has not seen one in November for almost 40 years. And so it was right off the coast of Alaska here. This is the Bering Strait. And we can look at the temperatures, not the temperatures, I don't know why I keep saying that. These were the peak wind gusts through 7 a.m. on November 8th, 2011, and these are in miles per hour. So here's 81 miles per hour, 85. Let's just blow this up a little, and you can see 81, 85, and this is over the water. It's higher, like in a hurricane. The wind speeds are higher than when they hit over water than when they hit land, and then they start slowing down. Here's 70 miles an hour, 60, and so forth. 62, 64, 66, 53, 76, 74, and then it quickly goes down when it gets on the land. 55, 24, etc., etc. So those are quite high numbers. We're not seeing miles per hour like that. We're not seeing miles per hour anywhere like that. So, and we'll advance forward in Earth Null School to see what they say. But I would not consider these storm systems we're looking at as cyclones. Anyway, to continue, this system was one of the more powerful storms to affect western Alaska since 2004, though the storm in October of that year had a track that was farther west over Russia. The track of the 2011 storm was similar to a major storm in November 1974, which moved north over the central Bering Sea across the Bering Strait to the Lisburn Peninsula. While the damage from this particular storm was not intensified by a lack of sea ice, researchers say that declining sea ice cover is already adding to coastal erosion in the Arctic. So these are tidbits of good information, that declining sea ice cover is already adding to coastal erosion in the Arctic. So they're talking about the sea ice like all around that northern part of Greenland and all the little cubby holes of Canada, that now they're going, with the sea ice moving back so much this year, then it won't be thick enough. You know, if we have early storms, you know, before it has time to refreeze to any kind of thickness, that's going to be a problem, and so it's going to add to coastal erosion. A recent study by Trina Overeem and colleagues at the University of Colorado showed that as the period of open water along the coast of the Beaufort Sea has grown longer, the rate of coastal erosion has sped up. For more on coastal erosion, see the Ice Lights article, Sea Ice in the Arctic Coast. So that's from National Snow and Ice Data Center. Now, here's from Hypothetical Hurricanes Wiki. Arctic Cyclone. An Arctic cyclone is a polar area of low pressure in the North Pole region with a hurricane-like structure. Like all northern hemisphere cyclones, Arctic cyclones rotate counterclockwise. Arctic cyclones receive names when they receive winds of 35 miles per hour, just like tropical cyclones. The Arctic Basin is considered to include all regions north of 55 degrees north latitude. Okay, so here we got a definition. They receive a name when they get winds of 39 miles per hour. So let's remember that. So that's what designates, I guess getting a name designates it's an Arctic cyclone. I don't really know. I mean, I couldn't find much to really tell me what an Arctic cyclone was. The Arctic Basin is considered to include all regions north of 55 degrees north latitude. They are considered Arctic cyclones with hurricane-force winds. Stronger Arctic cyclones can produce blizzard conditions, whiteouts, and very strong winds. Because they are most likely to form around Christmas, 2 rotating Christmas-themed name lists are used. So, anyway, there's that. So here's what it looks like. And this is an Arctic cyclone. It looks tighter. It looks a lot more condensed. It's got a lot more air coming into it, and so what we're looking at over at Earth Null School, I think, is a mini version of that. It's a mini version. Until 2015 to 16, polar cyclones were not named, so little is known about the basin's records. It is estimated that the 1997-96 polar cyclone season was the most active in recorded history, with estimates for that season ranging between 27 and 30 storms and 14 to 16 cyclones. So what we might be seeing up there are polar storms, and they could be large polar storms, but they're not cyclones. So I apologize for, you know, if anybody thinks it's cyclones, because I didn't know that, and I was just reading and, you know, kind of reporting on what other people were saying before I thought it out and had time to research it. This could be a clue that El Niño seasons are generally more active. Yeah, I'd say. According to most scientists, however, La Niña, El Niño, and neutral conditions have little effect on the basin. Activity is usually greater when water temperatures are roughly 35 degrees Fahrenheit. Activity is suppressed when waters are warm or frozen. Activity in the basin typically begins in early November and slowly increases until around Christmas, when it breaks. But after Christmas, a rapid decline in activity occurs. Strong cyclones in January are very rare, although there have been exceptions. And then they go through all the months and this and that. So, and here's the list. And, you know, they call them, they're all Christmas related since they happen around Christmas time. Angel, bell, candle, donner, eggnog, fir, gingerbread, holly, icicle, jolly, Chris, lantern, Mary, nativity, occasion, poinsettia, ribbon, sleigh, turkey, vacation, and wreath. And then they have a different list for odd years. So anyway, then they retire a name. So if you'd like to read more about the Arctic cyclone on that website, I will leave the links below to all of these. And now, this website was probably one of the most useful from Weather Online, and this is called the Beaufort Scale. And this was a scale, okay, I'll just read this. The Beaufort Wind Scale is a standard scale running from force 0 for calm to force 12 hurricane and above for the description of wind speed. Each value represents a specific range and classification of wind speeds, with accompanying descriptions of the effects on surface features. It was originally developed as a system for estimating wind strengths without the use of instruments. It was introduced in 1806 by Admiral Sir Francis Beaufort of the British Navy to describe wind events on a fully rigged man-of-war frigate of the period, and it was later modified to include descriptions of effects on land features as well. It is currently still in use for the same purpose as well, to tie together various components of weather, wind strength, sea state, observable effects into a unified picture. So here's the Beaufort Scale. I wish it were larger. But 0 is calm, 1 is light air, and you'll have ripples and no foam on the sea, and the wind speed is 1 to 3 knots or 0.3 to 1.5 meters per second. Force 2 is light breeze, small wavelets, smooth crests, and glassy appearance. 4.6 knots and 1.5 to 3.3 meters per second. Force 3 is a gentle breeze, and you'll have large wavelets, some crests break, and some white horses. 7 to 10 knots and 3.4 to 5.4 meters per second. Force 4, moderate breeze, small waves, frequent white horses. That's 11 to 16 knots and 5.5 to 7.9 meters per second. Force 5 is a fresh breeze, and you'll have moderate, rather long waves, many white horses, and some spray. 17 to 21 knots or 8 to 10.7 meters per second. Force 6 is a strong breeze, some large waves, extensive white foam crests, and some spray. And you'll have 22 to 27 knots and 10.8 to 13.8 meters per second. Force 4 is near gale. You'll have the sea heaped up, streaks of foam blowing with the wind. That's 28 to 33 knots and 13.9 to 17.1 meters per second. Force 8 is a gale. Fairly high and long waves, crests breaking into spindrift, blowing foam in prominent streaks. 34 to 40 knots, 17.2 to 20.7 meters per second. Force 9 is strong gale, high waves, dense foam, streaks in wind, wave crests topple and roll over, spray reduces visibly. 41 to 47 knots and 20.8 to 24.4 meters per second. Force 10 is a storm, where you have very high waves, overhanging crests, dense blowing foam, heavy tumbling sea appears white, and visibility is poor. There you have 48 to 55 knots and 24.5 to 28.4 meters per second. Force 11 is a violent storm, where you'll have exceptionally high waves, hiding small ships, sea covered with foam, crests blown into froth, and visibility poor. 56 to 63 knots, 28.5 to 32.5 32.6 meters per second, and 12 is a hurricane. The air filled with foam and spray, sea white, visibility extremely bad, and this is anything greater than 64 knots or greater than 32.7 meters per second. So let's compare that. Now that we know a little bit more about cyclones, I'm going to move this over so we can have our chart on the right. And let's compare some of these speeds. Well, first of all, before we do that, well, no, we can go ahead and do that. Okay, well, let's go back to today. And right now, well, where my little air, well, let's look down here where it's red off the tip of Greenland. That's 24.7 meters per second. And I'm gonna make this one smaller so that we can have both up at the same time. So this is where we're at today. Down here on the tip of Greenland, this is 24.7 meters per second. And so if we look at our chart over here, 24.7, that's in the storm range. That's a force 10. So that's off the tip of Greenland. And that also equates to 48 knots or 55 miles per hour or 89 kilometers per hour. Okay? So that's in the storm range. $24.7, right. That's not a hurricane, and it's not a cyclone. Okay, here, down here by Svalbard, that's at 14 meters per second, and that's within a near gale. That's force 7. Alright, you're with me? Let me close this up a little more. Now we've got both. You can see it side by side. Let's look up here. Here's 16.4, 15.2, 19.3. Let's look at 19.3. Move this over a tiny bit. 19.3. That's a gale. That's force 8. So that's fairly high in long waves. (43 miles an hour) and 70 kilometers per hour. So you get the idea. So let's pull our chart back up and let's move through so that everybody can see. Here we are at tomorrow, this time tomorrow, and we can see that the one kind of northeast of Greenland is starting to form, and it's not tight in like a hurricane, but it is in that circular motion. It is in that comma motion. Oh, I've got one more article to share. No, I don't. I'm sorry. I thought I did. Weather facts. No, that's miles per... that's a conversion, and that's air pressure. Move that back over. So there it is tomorrow. Let's see what the speed is. That's 18.5, 16.8, 17, 13, 15, 16, 18. So the highest one I got was 18.5. 18.7. So looking over here, that's a gale. That's at force 8. And that's 42 miles an hour. And there's no sea ice there. But on the area where it's coming around, there is sea ice. So it's coming around at 16 miles an hour. And that's 7.1 meters per second. So that's a force 4. So it's hitting the sea ice at a lower force than where it's coming around over Svalbard. So it's 7.1. Right, that's in this 4. Moderate breeze, small waves, frequent white horses. And then up here we can see this one coming off of Siberia has already shifted, and there's actually a hole here. And then it splits. It's kind of splitting in two. So let's check the speed here. That's 13.1 meters per second. That's a strong breeze. That's not a cyclone, folks. So let's move to the next day and see how things develop. We can see this now we see something gathering off the East Siberia Sea. Now it's gathering, so maybe it just got delayed somehow. So this is circling. It doesn't look real strong to me. 10.4, 12.4, 12.7, 12.7, looking at our chart, is a strong breeze. That's at 4.6. And then it's gathering over here. It's not tight. It's a large storm. It's a large area. And so where it's the fastest, I'm trying to find where it's the fastest. It's the fastest as it heads around. After it's gathered momentum all the way around, it's usually the fastest right before it feeds in. Okay, now it's going down. I saw a 14.4. We'll go with, I saw a 14.4. Let's go with that. So that's a near gale. That's a 4.7. .30 miles per hour. Now, where it's coming over the sea ice, let's see what the temperature is. I mean, what the wind speed is. 21 miles an hour. So that's quite a difference. 21, 21, 18, 18, 23. But it is warm air. Here's 27 miles per hour. So it is warm air. And we do have something forming down here in the Beaufort. This has moved around. So let's look at the wind speed. There is 26 miles per hour. So that's 11.8 meters per second. That's a strong breeze. That's 4.6 on my chart. So I'd like for people to calm down about the cyclone thing. And then by the second, you can see that it's kind of, everything is shifted. Everything is shifted. It's not as strong. And well, now it's tightening up a little bit. Let's see how, that's 11.2, 11.8.2, 13.4, 12.9, 14. That's the fastest reading I got on wind. So 14 is a near gale. That's a 4.7. But there's no sea ice there to break up. And we can see that this system is really kind of just spreading out and losing its steam, I think. There's 10.7, 10.2, 10.4, 7.6, 7.6. Now this is going right over the North Pole, it looks like. So this is going, swinging around right over all of that ice over the North Pole. So it just depends. And it could be raining over there, or it might be snowing when this happens. You know, we can do another layer, but I'm not quite finished looking at this. This will go up 5 days, and so by the 3rd they're here's what it's looking like by the 3rd, and we see we have a new system forming down here to the east of Greenland. And this is fast, 23.4. 23.4, that's a strong gale. That's a force 9 on my chart. It's around 24 or something like that. And but our systems up here are fizzling out. They're still going. I mean, stuff is still happening, but it's not a cyclone. It's just not. 9.9, 10.4. Here's where these all have fizzled out. 8.0. These are meters per second. 7.2. 8.0. And according to our chart over here, like an 8.0 is a fresh breeze. And then below the 8 is a moderate breeze. So we can stop worrying about cyclones up there right now, okay? We have enough to worry about. We just have enough to worry about without worrying about cyclones. So a part of me is a little bit sorry that I did that post, that last post that I did, because, you know, I wasn't educated on cyclones and storms in the North Pole, but now I am, and now I'll know what to look for, and I'll know if someone is getting worked up and trying to alarm us. Now there is low pressure here. We can see that, and maybe what Robert Fanny was doing was interpreting the low pressure. And we saw in that one article that sometimes you can confuse an Arctic low with low pressure. In this one, where it says, okay, low pressure, polar cyclones are large areas of low pressure, not to be confused with polar lows. It says a polar low is a small-sized and low-lived Arctic pressure, atmospheric low-pressure system that is found over the ocean areas poleward of the main pole front in both of the northern and southern hemispheres. The systems usually have a horizontal length scale of less than 1,000 kilometers. It sounds like that's what he was looking at and calling it a cyclone. Okay, I think that is what he was looking at, and so now we know. The systems usually have a horizontal length scale of less than 1,000 kilometers and live for less than a couple of days, and that's what these are doing. They are part of the larger class of mesoscale weather systems. Polar lows can be difficult to detect using standard weather reports and are a problem to high-latitude operations such as shipping and gas and oil platforms. Polar lows have also been known to be by using many other terms such as comma cloud, mesoscale, polar mesoscale vortex, Arctic hurricane, Arctic low, and cold air depression. Today the term is usually set aside for the more energetic systems that have near-surface winds of at least a gale force of 17 meters per second. So that's what we saw. We were seeing 17. Saw a lot of 17s. So here is the mean sea level pressure, and it is 993. That's almost 1,000 HPA, and that's just not very much lower. Here's 996, 997, 1,003. So even the 1,000 is in the purple zone. So you can't go by that. You just can't go by that. 1,001 HPA. So let's take the alarm out of that last forecast, and I'd like to wrap this up. I've been going a long time because I like to teach everyone, as you know. I teach people as I go because I want us to understand so that we are not deceived, and so that we can discern and we can see exactly for ourselves what's going on, and so that we can make our own decisions. Okay? So this is an example of being caught off guard and not knowing exactly what the data is. Seriously, what is the data? And what does it mean? And we need to educate ourselves. Okay? So, I know everyone likes to look at methane, so I've got cams pulled up. This is methane on the from the North Pole, looking down on the North Pole. Our base time is from, our last data is from Monday. And we can see a lot of the world here, so we'll just leave it on this view. I've already got it fired up. Well, I thought I did. Yep, here you go. And I'll let you look at methane as we close out. This is all in the forecast period. Look at how they're forecasting all this red over the Arctic. That's incredible. So methane is being released out of the Arctic Sea now, out of the Arctic Ocean. We can see these long streams of it. So this is just a fact of life, folks. Here we sit. And that red is around 2,000 parts per billion. The bright red. The darker red is 2020, the brick red is 2040, and then the black, it says, is 75,600. That's the highest it'll go up to on these readings. And we can see, you know, this whole area is just covered up in it. So, I love you guys. My name is Margo. My website is margoshealingcorner.com, and we will have a campfire chat next Thursday. Not today. Next Thursday. So until next time, get your spiritual houses in order. There's a lot going on, and time is very short. I love you. God bless. Take care. Until next time, goodbye. Go in peace.